Hello everyone, welcome to our Egyptian online seminar group. First, keep your microphones off. Then, if you have any questions, you can ask our speaker during his presentation or after his presentation. I have great pleasure of welcoming Professor Stephen Young. Stephen Young is a professor of accounting and assistant dean resources at Lancaster University Management School. His current research interests combine aspects of financial communications and natural language processing. His industry research preparation, including the Financial Conduct Authorities, the Financial Reporting Council, the CFA Society UK, and the Pensions and Lifetime Saving Association. He is an associate editor for Journal of Business, Finance, and Accounting, and an editorial board member for a range of journals, including accounting organizations and society, and accounting and business research. His work has been published in top-ranking journals in accounting, such as the Accounting Review, Review of Accounting Studies, Accounting Organization and Society, Journal of Accounting and Economics, Journal of Banking and Finance, Journal of Business, Finance and Accounting, British Accounting Review, Accounting and Business Research, and European Accounting Review. Now we will start our seminar with Professor Stephen Young.
Well, thank you very much, Mohammed, for that very generous introduction, and thanks everyone for giving up your afternoon. I hope the next hour or so is going to be interesting. I'd encourage you to ask questions as we go. So I'm happy for you to stop me and interrupt. That's absolutely fine. If you want to use the hand up function, you can do, or you can just unmute and interrupt. Don't worry, it's not a problem. If you don't want to ask a question directly, if you want to use the chat function, you can type a question into the chat, and I think Mohammed will monitor questions in the chat, and he'll stop me if he thinks there's a question I need to answer. Okay, so I can't see the chat when I'm sharing my screen, but Mohammed will monitor that. Okay, so I'm going to share my screen. So I hope that you will be able to see this. Can you let me know, Mohammed?
Yes.
You can see that. Great. Okay, excellent. Right. Okay. So this is a very, very preliminary paper, and it's a bit of a sort of voyage of discovery for myself and the team I'm working with. I'm not a natural language processing academic by training, and so I'm kind of learning as I'm going. And this paper is really started off as a learning exercise for us that's then kind of grown into a piece of empirical work that we've learned a lot from, even if other people don't think it's very interesting. So in that sense, it's been useful. We've also produced a set of materials associated with this paper. So if you go to the SSRN link for the paper, you'll see that the resources that we use in this paper, so the data sets and the Python code for all the tests, that's all available. So if you want to play around with what we've done, if you want to replicate things, or you want to use some of the algorithms in your own research, that resource is there. We're kind of updating it as the paper progresses, so it's probably going to change over the next 6 months, but you may find those resources useful. And I should say that the papers with my colleagues, some of whom are from Lancaster, from the computing department, so that's Paul Rayson and Andrew Moore, and then colleagues from Manchester, that's Martin Walker, Thomas Schleicher, and also Vasiliki Anastascu, who's now in Canada. Okay, so a brief summary of what we're going to do. So if you want to tune out after the next 5 minutes, you can do, and you'll still have a pretty good idea of what we've done. So our motivation and our questions are very simple. We're interested in answering a pretty fundamental question when it comes to the scoring of text using automated methods. And that is, to what extent can the methods that we see typically used in the accounting research replicate human judgment? So we're going to test the extent to which a range of classifiers, word lists, and machine learning algorithms can replicate how humans would code text for a small set of discourse features. And the features we're going to look at are tone, causal reasoning, and the source of the causal reasoning. So whether management is talking about internal factors or external factors that explain performance. So so that's our first question. Then a natural extension of that obviously is, which is the best method, and which methods work well or seem to perform poorly in particular situations or for particular discourse features. And so what we're able to do with these two questions, hopefully, is give you some insights into the absolute accuracy and also any bias that's associated with these methods. And we think that's quite new, because not a lot of work has shown the magnitude of measurement error associated with these methods. And then we're also able to show you some relative performance as well. And there is some work out there on relative performance of classifiers in accounting, but it's quite limited. Okay, what do we find? We find that regardless of what automated method we use, so whether it's a machine learning classifier or a word list, we're going to generate quite significant measurement errors, and the size of the measurement error depends on the discourse feature that we're looking at. So so even the best classifications that we do, we're only getting about 80% accuracy. So we're having to live with quite a lot of measurement error. And that's potentially important because one of the reasons for using automated methods is the notion that you can get higher power tests. And what we're going to show you is that actually with some of these methods, that they generate quite a lot of measurement error. So it's not obvious that you're going to generate a higher power statistical test. We also are going to show you that there's no single best method, which is kind of not surprising, but I think it needs stressing. So the method that will work best is really hard to specify ex ante. And it's going to vary depending on the text feature that you're interested in, and it'll probably vary according to the data set that you're using. So I think one of the things we found in our research is that you really need to start off with a suite of classification methods, and then narrow those down to the one or the two that work best. It's really hard to specify ex ante which is going to work the best. And then finally, we're going to conclude that although the direction of empirical research in accounting is much more towards large sample automated analysis of text, and sort of manual coding is now becoming quite unfashionable. We think our results highlight the fact that actually there's a really important role for manually coded data and studies using manual coding techniques, and that we shouldn't just ditch that approach to research as being invalid because we've got some fancy automated methods. I think the more that we work with automated methods, the more it makes us realize the benefits of manual coding. And so we would see automated approaches and manual coding as complementary rather than as mutually exclusive alternatives. Okay, so what's the motivation for our work then? So if you look at accounting research over the last 10 years, you'll have seen this dramatic rise in studies that use automated methods to measure characteristics of text or to develop measures based on text. So for example, something like the probability that a firm will commit fraud. So this automated processing of accounting text has really started to get traction over the last decade, mainly since Feng Lai published his sort of seminal paper in the JE in 2008, looking at readability. Since then, things have moved quite rapidly. And there's good reason to suspect that there are significant benefits associated with large sample automated analysis of text. And those advantages are articulated by Lai in his review paper in the Journal of Accounting Literature. So he's got a really nice paper that reviews the literature on narrative reporting and qualitative information. And he identifies 4 key reasons why automated processing of text is potentially valuable. And these 4 reasons kind of resonate, I think, with all of us. We recognize the potential benefits of automated analysis. So the fact that it's potentially much lower cost, particularly if we're using an off-the-shelf method for scoring our text, such as a word list. So it's pretty low cost to take a Loughran and MacDonald positive and negative word lists, apply them to text, and come up with a measure of tone. So it definitely meets the low cost criterion in many respects. In addition to that, there's always been concern with manual coding that there's a high degree of researcher subjectivity, which means it's hard to replicate the results. And of course, that's always led to some suspicion about manually coded analyses that, well, you know, can we replicate them? And do we really understand the choices that researchers have made? And even if there are not explicit biases, then maybe there are subconscious biases that the researcher has included in the analysis, and that could lead to bias tests. So the fact that we can apply an algorithm, which is potentially fully objective and free from any researcher subjectivity, means that we get more objective tests that are potentially more replicable. Okay, so again, it seems to meet the objectivity and replicability criteria. Higher statistical power is also frequently identified as a benefit of automated methods, because we can apply the scoring to very, very large samples. And once we get large samples, then we start to get the benefits of more powerful statistical methods and more powerful statistical designs. So this statistical power argument is pretty well understood and pretty well accepted. And then because we can scale our measures of text across very large samples, it means that we get greater generalizability potentially, because we can include more firms in our sample, and therefore we're more likely to be picking up a representative set of firms. So these benefits are kind of what's probably driving a lot of research that's starting to adopt automated methods. And you see these arguments being made regularly when you read papers that are justifying why they use automated methods. And I think there's a danger that we take them as axiomatic and we don't think a little bit more carefully about, well, are these really true in all situations? And so that's what really we've been reflecting on when we've been using these methods. The more we've used them, the more we've started to think about, well, are all these proposed benefits true automatically? And our conclusion is, well, not necessarily, no. So these methods, for example, are not necessarily lower cost, particularly if you're involved in some sort of machine learning training algorithm where you have to code up a large amount of training data. That's still a pretty high cost activity. The methods are low cost when you're applying very simple methods in a very simple setting. But of course, the danger with that is that that's the least interesting approach. Subjectivity and replicability, well, at one level, of course, they are objective because we're using an algorithm. But there is quite a lot of subjectivity involved in these methods because there's a lot of choices, particularly with machine learning algorithms that sit in the background that are not really brought into the spotlight. And so there's a danger that we think that research is very objective and highly replicable, when actually there are a lot of research choices going on in the background with automated processing that we're just not seeing. So that's true of both when we apply classifiers, but also when we process the text. So choices like, have we removed stop words? What stop word list have we used? Have we applied a stemmer? These sorts of choices, you quite often see them being glossed over in many papers, but they can make a huge difference to the results. So automated processing does not automatically mean more objective processing in our view. This question of high statistical power, that's kind of probably where our main focus is today. There's this idea that because you've got a large sample, it's going to generate a better statistical test. Well, of course, that's an all else equal statement. But all else is not necessarily equal with automated processing methods, because you may be getting lots of measurement error. So the benefits that you generate from moving to a large sample setting could be offset by the costs of very, very high measurement error. So it's not automatic that you're going to generate higher statistical power tests. So there's a range of issues really that we've been reflecting on when we've been doing this work that have made us think about, well, maybe we should go back and we should ask some fundamental questions about just how good are these methods relative to manual coding. And in what sort of situations do we think we can rely on them? And in what sort of situations might we have some concerns? And might we even come to the conclusion that a manual research design is still the best? So that's kind of the background of our paper. And in order to do this, ask this question, we're going to focus on just some very common discourse features that appear in accounting research. So we're going to look at how we code tone automatically, and tone is the most popular discourse feature that we see in accounting research. And another popular feature is causality or causal reasoning. So managers justifying performance and results because of certain events or outcomes. So that causal reasoning element is also quite popular. And of course, if you put those two together, that takes you into the area of attribution bias, which has attracted a lot of attention in prior work. So the idea that managers are more likely to cite internal factors for good results, whereas they're more likely to identify external factors such as the weather or interest rates or general macroeconomic conditions to explain poor performance. So these are the features that we're going to use as the basis for our analysis. Of course, lots of other features can be coded automatically. So our study really doesn't say anything about any other types of automated coding other than if you want to code tone, you want to code causal reasoning, or you're interested in measuring attribution bias. So it's important to stress the limitations of the insights we're going to provide. We're not going to be able to make general statements about all types of automated processing for all applications. And we're going to contrast two generic approaches to classification that are commonplace in the accounting literature. Word lists, which is arguably the most common approach. So this is where researchers take a predefined list of words that are associated with a particular construct they're interested in, and then they count the incidence of those words within the text, and then they use those counts to construct a measure. So for example, around tone, we would count the number of positive words and the number of negative words, and then we would take the difference between those two, and that would give us an indication of the polarity of the text. Okay, so word lists are very popular. Less popular in accounting, but becoming increasingly more mainstream is machine learning. So this is where we've got an algorithm that learns the characteristics of the text that are important for distinguishing between categories. And then once we've learned those characteristics, we can then use those characteristics to build a model that predicts out of sample. So machine learning classifiers are sort of standard approach in natural language processing amongst my computer science colleagues. That's what's done all the time, but it's not the go-to method in accounting research, and that's kind of quite odd, really. So accounting research tends to focus on word lists as the sort of default approach. And the argument there is because it's easy and it's transparent. But if you look in the computer science literature, you know, none of my colleagues in natural language processing think word lists by themselves are particularly successful for classification. You know, they're all using some sort of algorithm. And so there's this disconnect really between what we see in accounting as being defined as cutting edge and what we see in the core discipline, natural language processing, as being defined as cutting edge. And the accounting literature is kind of a long way behind the cutting edge in natural language processing. And so it's an important question of whether word lists are okay, or whether actually we should be moving to more sophisticated algorithms because word lists are unreliable. So that's what we're going to do. We're going to compare those two generic approaches, and we're going to build on a very small number of papers that have tried to provide some insights around the performance of different classification techniques, but it is a very small number of studies. So Lai provides a little bit of information on accuracy of his machine learning classifier, but he doesn't compare it with any other methods. So he shows that his naive Bayes classifier is about 60% accurate for coding tone in forward-looking statements. So that's an absolute indication of performance in one setting, but it doesn't give us much information about kind of relative performance. Then Loughran and MacDonald compare different approaches to measuring tone. So in particular, they construct a domain-specific word list for positive and negative outcomes, and they compare that with a generic unspecific language dictionary. And they show that it's actually really important to use domain-specific word lists in areas like accounting. And so the classic example of that is a word like liability. So liability has negative connotations in general language, but it's just an element of the financial statements in accounting, and it doesn't have any directional implication. So distinguishing between that is quite important. And then Henry and Leone take it a little bit further. They compare the Loughran and MacDonald word list with some word lists that Elaine Henry produced herself, much more parsimonious word lists. And they also do a comparison between word lists and a naive Bayes classifier. Okay? And they conclude that word lists do pretty well. They're not quite as good as the machine learning classifier, but they are close, and they are much easier to use, much lower cost. So therefore, their results kind of speak to the justification for using word lists over more complex classifiers. Okay, so just a little bit about how we might assess performance, or how it's done in prior research, and then how that informs our research questions. So there are two approaches to thinking about the quality of performance measurement. The first one is we can do direct comparisons between manually coded data and the results of our learning algorithm. So that's the standard approach in natural language processing, but it's rarely used in accounting. So Lai's paper in JAR is one of the very few papers where he compares the outcome of an algorithm with manually coded sentences. And as I say, he comes to the conclusion that the algorithm does okay, but it's not great. It's about 60% accurate. So depends whether your glass is half full or half empty. 60% maybe quite good. It's enough accuracy to answer your research question, or it might be quite bad. 40% measurement error is pretty inaccurate. So the kind of jury's out really with his result. The alternative approach, which is what we see used more commonly in accounting and finance studies to assessing the validity of a text construct, is this kind of regression framework where it's an association test. So the idea is that we construct our text measure, and then we run a regression where we regress that measure on a set of covariates that we think should correlate with the text measure. And the extent to which they correlate is an indication of whether our text construct is capturing features, the kind of underlying features that we're interested in. So this association test, we're looking at the sign and the significance of the coefficient estimates, and we're looking at the R-squared of the regression. Okay, so we would conclude that a text construct is a valid construct if our covariates explain the text constructs in the direction we expect. So in other words, the beta coefficients load significantly and with the theoretical sign, and also that the regression explains a significant proportion of the construct. So we've got high explanatory power. So this kind of approach is standard in the literature. It's okay potentially for making statements about relative accuracy, because we can make statements about the amount of explanatory power, or we can look at the sign of the beta coefficients and maybe how significant they are. But you can't really make any statements about absolute accuracy and bias from this kind of empirical test. And the main reason for that is because we typically have no theory about what the correct coefficient estimate is on our covariates. So we may have a rough idea of what the sign is, but we can't theoretically specify a point estimate. And because we can't do that, we don't know how close we're getting to the correct number, and we don't know if we're measuring it with bias. So this approach tells us something about relative accuracy, but it doesn't really tell us much about overall accuracy, absolute accuracy and bias. So with that in mind, we're going to ask the following two research questions. We're going to try and answer the accuracy, the absolute accuracy and the bias question by testing the extent to which these a range of classifiers can replicate manual coding. So we're going to code some text. We're going to then score it using a range of classifiers, and we're going to see how good the classifiers replicate the manual coding. So that'll tell us something about absolute measurement error, and it'll also tell us something about bias. And then, of course, with that, we can also start to make some hopefully clearer statements about the relative performance of different approaches. So we can make statements about the performance of word lists versus machine learning classifiers generally. And hopefully we can give you some information on the performance of alternative classifiers, alternative machine learning classifiers, okay? Which there isn't really any evidence on that in the accounting literature at the moment, although there's plenty in the natural language processing literature. So that's our research questions. Okay, so what are the discourse features that we're going to code? Just to clarify, we're going to code sentence level tone. So we're going to read sentences manually. We're going to code them for tone, and then we're going to come up with ways of scoring those sentences automatically. And the ways that we're going to score them automatically, we're going to use the Loughran and MacDonald word list, which is the most commonly employed in the literature. We're going to use the Henry word lists, which Henry and Leone indicate perform better than Loughran and MacDonald. And we're going to use a suite of machine learning classifiers. And the machine learning classifiers we're going to use are as follows. We're going to use naive Bayes, random forest, SVM, and a recursive neural network called multi-layer perceptron. Now, if you look in the accounting literature, typically, if anyone uses a machine learning classifier, they use naive Bayes. So naive Bayes is the kind of default classifier in accounting literature. It's simple to use. It's a probabilistic classifier which uses the joint probability of words and the categories you're trying to measure to come up with a probability of what the category is. Okay, so simply applied, and it tends to be the baseline for machine learning classification. But if you go to the natural language processing literature, naive Bayes is just one of many classifiers that people can use. So sorry, so my cat decides that it's an opportune time to come and visit, so apologies. So we're going to not only use random forest, we're not only going to use naive Bayes, but we're going to use other kind of common baseline machine learning classifiers. So we're going to use random forest. Random forest is a non-parametric approach. It is based on the wisdom of crowds. So the idea is that you take a subsample of your data, you fit a decision tree to that data to link characteristics to the category you're interested in predicting. And then you repeat that process a lot of times. So you generate a lot of decision trees, and then you just average across the results for those decision trees. So it's essentially you're counting votes across a range of decision trees, and you pick the model which has the most votes. So so it tends to be pretty good. It's very good for avoiding overfitting in the data typically. SVM is an algorithm, a non-parametric algorithm, relatively sophisticated. The idea is that it's trying to identify the maximum split, the maximum degree of margin between categories that you're trying to classify. So imagine you're trying to classify positive and negative sentences. The SVM algorithm is trying to split your data in a way that maximizes the margin between positive sentences and negative sentences. And then it fits a hyperplane within the middle of that margin. And that process gives you the optimal way of splitting between the categories. And the attractive feature of the SVM algorithm is that you're not operating in a two-dimensional space, you're operating in a multi-dimensional space. So that hyperplane is nonlinear. So it provides a pretty effective way of splitting data which is not linearly separable. So potentially quite powerful. And then finally, we used this multi-layer perceptron. So as part of a class of artificial neural networks, it's, I mean, I'm not an artificial neural networks expert by a long way. So my basic understanding of this is that essentially what you're trying to do is you're trying to identify, you're trying to learn a model that can split data that is not linearly separable. So if you're dealing with a problem where the data doesn't split linearly, then you can use your multi-layer perceptron essentially to learn a nonlinear transformation of the data. And you can use that nonlinear transformation to then project outcomes into a linear space, which you can then classify. So it's almost like you come up with a nonlinear transformation and then you apply a logistic regression to classify. That's perhaps the simplest way of thinking about it. Okay, and the important thing with these machine learning classifiers is that theory doesn't really tell us which is best ex ante. So if you look in the machine learning literature, they're not really clear about which of these work best, and there's certainly no dominant model. So what you tend to find is that researchers will use a range of models to start with, and they'll pick the best. So that contrasts with what you see in accounting research, where we typically just go straight for naive Bayes and we forget about everything else. So hopefully we'll be able to present some evidence on whether naive Bayes is indeed the best model or whether we should be considering other approaches. Okay, so that's our suite of machine learning classifiers for sentence level tone. We're going to also classify causal reasoning. So this is sentences where managers are justifying performance. So they're saying, performance was good because of, or performance was bad due to. So that sort of causal reasoning indicator. So we're interested in identifying sentences that contain causal reasoning. And we're going to use word lists and our suite of machine learning classifiers again. the word lists we're going to draw from extant research. So one of the most popular word lists that we see used is this word list from Language Inquirer and Word Count software. So they've got a word list of causal words that a lot of research uses that list as the basis for measuring causal reasoning. So Lai used that measure in his JEE paper. Then we're also going to use a word list suggested by DeColey et al. So that's a more recent paper in Accounting Review. So they take the Luke word list and they augment it and improve it and come up with their own adjusted causal reasoning word list. And then we also construct our own causal reasoning word lists as well. So we've got some self-constructed lists, and then we apply our machine learning classifiers. Okay, and then the final text attribute we're interested in is the type of internal attribution. So are managers referring to internal features like strategy or cost control or reorganization, or are they referring to external features such as the weather or industry competition or other factors that are often seen as being outside their control? Okay, and here there really isn't any word lists available in the literature, so we have to construct our own word list, and then we're going to compare that with our suite of machine learning classifiers. So for each of these three discourse features, we're going to use the same suite of machine learning classifiers, and we're going to compare that with discourse specific word lists. Okay, now I've in addition to my drawing all over my my slides, I've also got somebody else's drawing all over it. So I'm just going to come out of this so that I can get rid of it. Okay, so and I'll share my screen again. Okay, let me. Okay, so hopefully you will be able to see. Oh, just bear with me a second. There we go. Okay, let me go back and share my screen. Okay, there we go. So I've got rid of all annotations. Okay, so good. So there are discourse features. Our research design is as follows. We're going to start with a training sample, and so that's our manually annotated training sample. And what we're trying to do here is make sure that our manual annotations are objective and verifiable. So we manually code sentences, but we use a double-blind scoring approach. So every sentence is scored by two researchers working independently, and then we compare the results. And if there's any inconsistency, we then use a judging process to clarify what the appropriate classification is. And if we can't identify the appropriate classification because it's too ambiguous, then we drop the sentence. Okay, so we're trying to make sure that our manual coding is replicable and objective. So once
Stephen, I have a question for you.
Yeah, please.
So, I took a look at your paper. So this is Chris Ali. Nice to meet you. I'm from the University.
Hi.
So I do some research in this area, and one of the questions I had about your study, I was trying to look at it on SSRN. Where do you get these sentences from? Like, what's your data?
Okay, so I've got that on my next slide.
Okay.
But it's just as easy to answer your question now. So we're going to use earnings announcements by UK firms. So when firms announce their performance, typically their earnings, they make an announcement to the stock exchange. And that comes as either a HTML or a text file that you can collect if you've got a subscription to a particular service. So we collect a range of these documents, And then we're going to pick out sentences that we think are performance sentences. So we don't just code any sentence. We're going to use a very simple approach to filter the sentences. So we're going to use a set of what we call performance keywords. So words that we think managers will use when they're talking about performance. And we're going to pick any sentence that includes that word.
So you basically, I guess my question, and again, this is why I'm asking is, so I have a paper where we look at like how accessible is text and how easily is it for a computer to basically access information, right? And so one of the things that I struggled with the study is, in my study, we find that it's actually very hard for computers to read stuff. Like if a company reports a 10K or an 8K or a Def 14A or whatever it is in the US, right? Or in your case, if the company sends out this HTML or this text document, right? Like ultimately identifying the sentences that it is that the computer is supposed to identify to then use textual analysis or naive Bayes or whatever it is. Like that can be actually a difficult task oftentimes for the programmer and also for the computer who's programmed by the programmer to do. And so one of the things I think that your paper would be good is, you start out at the assumption that you can get the sentences, and a computer can only do that if it can do that, right? And so anyways, something I noticed.
No. So Chris, you're absolutely spot on. And that pre-processing level for text processing, it is absolutely critical, and we've found that to be the case as well. So
but you're pretty silent to it in your paper, and again, I just looked at the paper on SSRN, but all the pre-processing that it takes, we call it disclosure scriptability, right? The scriptability, the descriptability of getting to that level on a computer automated process is actually pretty significant.
It's a massive task. You're absolutely right. And so the way we're going to deal with that in this paper is it's pretty easy for us to get the text out of the HTML. Okay, so that's straightforward. It's a non-trivial task to split the sentences, but we can probably live with some of that, particularly because these earnings announcements, that they don't really have any sophisticated formatting in. So you can split the sentences reasonably well. But then your point about how do you get to the relevant sentence is like the key one for us. And so the way we do that is we start off with this set of keywords that's gonna pick up a whole bunch of sentences that we think are related to performance. But we're going to cast our net widely. So we're going to specify a set of keywords that's going to generate a lot of type 2 errors. So we're going to get a lot of sentences back that aren't performance sentences. Okay. But then what we're going to do is we're going to manually read each of those sentences, and we're going to manually classify whether it's a performance sentence or whether it's junk. And if it's not a performance sentence, we're then going to throw it away. Okay, so that's the best way we could find to get a reasonably accurate set of performance sentences that we could then start to train some algorithms on. Because you're absolutely right. That first stage of identifying the relevant sentences is a critical one, and it's one that's really difficult. And so we navigate around that by essentially doing it manually.
Yeah, I appreciate it. I just thought that, again, I didn't read your whole paper, but looking at your paper, I think you just need to acknowledge that.
Yeah. It's a critical point because it affects everything that subsequently
like human
comes.
versus machine, right? Like this exercise, and you have to start with a machine to get to the thing that then you're going to process, right?
Yeah. No, you're absolutely right, and it's a point really well made. So let me try and let me go back to my slides. I'll go back into slideshow and then share. Okay. So research design, we come up with our training sample. I'll say a little bit more about how we do that, which adds to what I've just said in response to Chris's question there. We do this manually coding. We do this manual coding to identify what we think is correctly classified characteristics like tone and causal reasoning. And then we train some algorithms, and the training process we use for these algorithms is pretty basic. So this is going to replicate what typically occurs or what we think typically occurs in accounting studies, because they often don't explain what they do. So the way we the way we train our algorithms is we come up with a very limited feature space. So it's very, very basic application of machine learning classifiers. So all that we're going to do is we're going to use n-grams as our the key inputs to our feature space. So we're still working here in a bag of words approach. So although we're using an algorithm, we're still really naive in terms of the way we're treating text. So we're just treating text as individual words, unigrams, or we have the opportunity to consider bigrams, okay? But nothing else. So we don't do any other feature space reduction. So we don't remove stop words. We don't remove excessively common words. We don't apply any stemming. None of those sorts of things that you might do normally if you were trying to develop an optimal classifier. We don't do that because it's not clear that that's what people do when they apply these methods in accounting. At least they don't typically explain that they do that. And then we don't include any other features that you might think might be important to improve classification accuracy. So you could, in addition to just using a bag of words approach, you could add range of surface level features to the classifier, like the number of words. We don't do that. We don't add any deeper linguistic constructs, things like the type token ratio or readability or any of these sorts of features. And we don't add any word lists to the classifier. So this is as basic a classifier as you can get. And we think that's appropriate for the purposes of our test, because we think that's what the majority of research in accounting that uses these methods does. Although, as I said, it's kind of hard to get at that because they typically don't tell you what they do. So I suppose a caveat with what we've done here is we are not developing the best machine learning algorithm for our discourse features. Okay, so the estimates that I'm going to show you are probably lower bound performance estimates on our classifiers, yeah, because we could do a lot more. We could probably make them better, but we haven't done. And that's probably something that we will explore in subsequent versions of the paper, I think. And then how do we select our algorithms? Well, that's a question of this hyperparameter tuning. So what we've got for each classifier is we've got a feature space that we can search across. So which unigram or which bigram or which mix of them do we pick, as well as a whole bunch of classifier parameters that we might want to vary. So in the case of naive Bayes, for example, we might want to compare a multinomial with a Gaussian or a Bernoulli classifier and see which works best. So there's a whole bunch of choices that go on in the background to determining your classifier. And the way we work with that is we run this hyperparameter tuning approach where we run 40 different versions of the model where we randomly select and randomly fix elements of the feature space and parameters in the classifier. And then for each of those 40 iterations, we look at the performance of the model using a tenfold cross-validation, and we measure the accuracy either using a simple accuracy measure or a macro F1 measure, which I'll talk about shortly. The results I'm going to show you, we're picking models using macro F1. So all that we're doing is for every classifier, we're essentially running 40 different versions of the classifier. We're comparing the performance based on macro F1. And for each classifier, we're picking the combination of features that gives us the best macro F1. Okay? So you don't typically see a lot of this discussed in accounting applications of these classifiers. So we don't know if that's what prior research does, but that's sort of standard practice in NLP. So that's our machine learning classifiers that we're gonna train those on the training sample. We're also going to develop our word lists, our self-constructed word lists using our training sample as well. And then, of course, we can see performance for the training sample, both for the classifiers, machine learning classifiers, and for the word lists. The problem with using the training sample to assess performance, however, is that it's data that's been seen certainly by the machine learning classifier. So it's data that's being used in developing the model. And it's also data that's being used when we develop our own word lists. So essentially they're in-sample tests. And of course, there's a danger of overfitting when we're dealing with in-sample tests. And so what we do is we construct another sample, which is what we call a holdout sample, where we code a new set of sentences using the same procedure. These are sentences that none of the classifiers have seen. So this is unseen data. And then we apply the classifiers to that unseen data. And that is going to be our main test of performance. Okay, so the results I'm going to show you are results on the holdout sample, not the training sample. Okay, sampling, which is to Chris's point. The way we do this is we're going to extract sentences from UK firms' earnings announcements. We're going to select for our training sample using a stratified approach where we select firms based on their change in earnings. So we're going to select some firms with very poor performance, some firms with very good performance, and some firms with moderate performance, just so that we avoid any bias associated with how language changes as performance changes. And our focus is on performance sentences. And so as Chris was pointing out, this is a non-trivial task in textual analysis, is how the heck do you identify a sentence in the text that is a valid performance sentence? So the way we do this is not an automated process, okay? Because we wanted to get this accurate. So the way we do this is we apply a word list using words that we think managers will use when they're talking about performance. So words like earnings and results and profit. So we pick all sentences with those words in, and then we go through those sentences and we manually determine whether they are valid performance sentences or not.
David,
yeah.
From Anisha, you can open your mic.
Sorry, Mohammed, I didn't get that.
Yes. Anisha, you can ask.
Oh, are you talking about me?
Yes.
Yeah, I have a question. I was wondering, why did you focus on 2011? Is there a specific event, or is there a reason why do you take 2011?
Okay, that's good. So it's a good question. Thanks for asking. There's absolutely no magic in us choosing 2011, other than the fact when we started this project back in 2014, and we wanted to collect reasonably recent data, and so we collected data from 2011 and 2012. So there's no magic about our selection of years. I mean, we're hoping that it's representative. Does that answer your question?
Yeah, well, I didn't know why was 2011 selected.
Yeah, there's no magic. There's absolutely no magic in this. It's just the data we had.
I see. Okay.
Okay, thanks. And then what we do, once we've identified these, what we call performance sentences, but of course they're not all performance sentences, there's a lot of measurement error here, is we're then going to focus on the adjacent sentences around our target sentences. So what we're actually going to code is 3 sentences. We're going to code the sentence that we think might be a target sentence, but we're also going to code the sentence before it and the sentence after it. And the reason for that is because often a performance sentence is contextualized by what comes before or what comes after. So getting some context for the sentence is really important when coding it. And also when it comes to features like causal reasoning, we often find that causal reasoning is in an adjacent sentence to when managers have talked about performance. So they don't always provide causal reasoning in the same sentence that they talk about performance. So if we want to pick up causal reasoning, we find that it's actually a lot of causal reasoning occurs in adjacent sentences, not necessarily in the target performance sentence. So we use this 3-sentence block for our coding. And that means we end up coding just over 26,000 sentences manually. And about just over 8,500 triple sentence blocks. So that's our training data. Our holdout sample, same idea. This time we use data from 2012. We just randomly select earnings announcements here. We apply exactly the same technique. So we select performance sentences using a word list, and then we go through and manually code them, and we throw away sentences that aren't valid performance sentences. Okay, so that's our sampling approach. What does our data look like? Well, remember our approach here. We've tried to minimize. We've tried to minimize the incidence of type 2 errors. In other words, we've tried to make sure we get all performance sentences using our word list. The price we pay for that is, of course, we're going to be pulling out a lot of sentences that aren't true performance sentences. And so we manually code them. So that's how we get rid of these type 1 errors. We read them, and if the sentence is not a valid performance sentence, we throw it away. And so what that means is, whilst we start off with a lot of sentences, we find that our word lists aren't very good at identifying performance sentences. They identify a lot of sentences that aren't performance. So actually what we get down to is a training sample that varies between about 3,000 and 7,000 sentences, depending on which feature we're interested in. So for tone, our set of sentences is just over 3,000. So it's about 2,300 that are positive sentences, and almost 800 sentences that are negative sentences. For causal reasoning, we've got causal reasoning present in about 1,500 sentences, and then we have about 5,500 sentences that are valid sentences for the purposes of our test, but they don't contain causal reasoning. And then for attribution type, so conditional on causal reasoning, we then look at what attribution type there is it internal or external? And we've got a roughly even split, about just over 7,500 internal attributions and 600 external attributions. It's important to note here that some sentences may contain both internal and external attributions. So managers might say results are great because interest rates were low and our strategy was fantastic. Okay, those sentences don't have any discriminatory power because they contain both elements. So we only retain sentences where there is either only an internal attribution or only an external attribution.
So is that true for the positive and negative sentences too? If there's
yeah, it is. Yeah, it is, Chris. Yeah. So the positive and negative sentences are sentences that manual coders have determined to be positive and negative. So they may have a positive sentence may have negative words in it, but the manual coder has determined it's nevertheless positive tone, and vice versa. So we throw away anything that is neutral. We throw away anything that has no tone at all or that is ambiguous. Which
again works for what you're up to, right? But ultimately is a huge limitation in what can be generalized from what you do, right? Because we all know that, as you said, attribution can be mixed, tone can be mixed.
Yeah. And so I suppose our response to that criticism, Chris, because I think it's a very valid one, is what we're trying to show is probably, almost like a best case scenario of how, if the world was very simple and processing was pretty simple, how good could it, how good can you get it? I think sorry, I'll just finish that point to Chris. So I think what our results for our classifiers show at one level, Chris, is that it's going to be much harder to get the sorts of classification accuracy that we're showing if you were doing a full automated pipeline with no manual intervention in it. So
Agreed.
in some respects, we're giving you the best case scenario.
And even then, it's really hard. So
exactly.
Depressing. It's depressing. Is what it is.
Exactly. And I think that's kind of why we wanted to do this work and show the results, because I think there's a danger, particularly amongst less experienced researchers, maybe PhDs, is that they see these techniques out there and the techniques look like science because they're sophisticated. But there's a real danger that actually all you end up with is just a lot of noise. And so it actually becomes quasi-science. You're using a range of sophisticated methods, but the constructs you're producing contain a vast amount of noise.
Stephen, I had a question about, are these performance that you are capturing here the first time that the firm are talking about, or are those like repetitive performance that we might find in other filings before you capture these earnings announcements?
So there's no conditioning. These sentences are just purely random sentences collected from the earnings announcement. So there's no sense that the firm has mentioned this information before. There's no sense that it's appeared anywhere else. It's, for our purposes, it is purely a performance sentence that we can unambiguously identify as being either positive or negative. That's it for our purposes. Okay, so we're not going to measure how important the sentence is. We're not going to measure whether the sentence contains price sensitive information. All that we're capturing is this a sentence that has some sort of tonal or polarity when talking about performance?
Okay, got it.
Hi, Stephen. This is Mohammed. Just have one more few questions. The first one here on the slide we see now, you classify the tone on positive and negative only. Is there any neutral tone?
No. So what we find is actually in our manual coding, we had a relatively small number of neutral sentences that were performance sentences. So I think we ended up with about 150 neutral sentences. So really quite low. And so the number was too low to have a separate classification class. Ideally we would have had positive, neutral, negative. Okay. But we just didn't have enough sentences in the neutral category to have reliable classification. So no, we get rid of those. So our classification is purely binary.
So another question, when you use the the word list, you will have to use for performance indicator or word list, and another one to classify is if the word is negative or positive.
If you wanted to do this in a fully automated pipeline, yes.
So you have two word lists. What's the two word lists you have used?
Okay, so the word list we use to identify performance sentences, that's in the paper. So that's a mixture of words that we identified as being associated with sentences that talk about earnings or earnings related performance. And it sort of builds a little bit on a word list that Lai used. So that word list is in the paper. The word list then we use for positive and negative. So they're drawn from prior research. So we're either going to use Loughran and MacDonald, positive and negative word lists, or we're going to use Henry, positive and negative word lists. Okay, so we're just taking those from prior research.
Okay, and I'm not sure if you heard about like supervised machine learning, which they use BERT, which is built by Google, and they use LSTM layers to read in double sides the sentences and identify the words in there and the meanings.
Yep.
I believe this should be more suitable and more accurate.
Well, so you're absolutely right. So sort of word embedding approaches are much more standard place in the natural language processing literature on sentiment. You're absolutely right. So what, just to clarify, what we're trying to do here, we're not necessarily trying to show you the best learning classifier for classifying tone. What we're trying to do is show you what is typically done in accounting research and how good is it. Okay, and word embedding is not typically done in accounting research, not that I know of anyway. The best classifiers that are used in accounting research are some pretty basic naive Bayes applications. Okay, so we're really just trying to replicate what prior accounting and finance research has done. But you're absolutely right. If we use more sophisticated learning classifiers, so maybe word embedding, maybe some deep learning models, we could get better results. You're absolutely right. And I don't dispute that at all.
So the sentences here, have you turned it to its vector in order to use machine, like to read the sentences and to read the vector of the sentences? So basically in machine learning, we have to turn the words or the sentence, each word into its vector.
Yep. So we just generate the term document matrix for each for all our text. So we just reduce sentences to a vector of words. Yep.
All right, thank you.
So either unigrams or bigrams. Okay.
Yeah, thank you so much.
Okay, fine. Yeah, so again, very simple. We're just operating at either the unigram or the bigram level. And we've got no other features that we're including in our classifier. Okay, they're the features for the holdout sample. So the holdout sample is a bit smaller. It's because it's very costly to manually code all this data. But we've got enough observations there to get some statistical significance. Okay, so classification performance, first of all, across our models. How do we do it? Well, we focus on a simple accuracy measure. This is what you see often quoted in accounting papers. So we're just the number of sentences correctly classified over the total number of sentences. But then obviously it's more sophisticated than that. So we move to some class level performance measures. So we're interested in precision and recall, which are the standard metrics that you see in natural language processing. So precision tells us, conditional on coding a sentence as positive, what proportion do we get right? Okay, so let's say we identify 100 sentences as positive. How many of those sentences are actually correct, are actually positive? So that's precision. Recall is a test of how many of the total number of sentences in the category are we able to capture. So let's say there's 150 sentences in our data set that are positive. How many of those 150 sentences are we able to capture with our measure? Okay, so that's recall. And if you put those two together and take the harmonic mean, you get this F1 score, which kind of averages across precision and recall to give you a class level performance measure. And so that would be, you know, your accuracy of identifying positive sentences or your accuracy of identifying negative sentences. And then we can average across those classes. We can average across those classes to produce what we call macro F1, which is the total classification accuracy across the classes that you're trying to classify. Okay, so we're going to be focusing on precision, recall, macro F1, but we're also going to report accuracy statistics as well. And you'll see in a moment why differentiating between these is important. Okay, a quick summary of which learning algorithm is best. We compare across our 4 algorithms. We select the best one, and we use that in our holdout sample. So I'm only ever going to show you the best performing machine learning classifier to compare with word lists. What we find is in our tests, our applications, naive Bayes is never best. So it's always dominated by at least one of the other classifiers. So the fact that we typically see accounting researchers defaulting to naive Bayes as being the classifier of choice, I mean that's quite a rookie error, because you know, it's not guaranteed to produce the best results, and in our tests it never produces the best results. So I think if we were going to provide some simple advice to accounting researchers who just wanted to do some basic machine learning classification, is you should look at other classifiers as well as naive Bayes before you make your final choice, because there's nothing magic about naive Bayes, and you're probably getting results that are less accurate simply by focusing on that one classifier. Okay, let's look at our results now for our holdout sample. So tone. So the classes that we're trying to classify, we're trying to classify positive tone, and we're trying to classify negative tone. Okay, so 2-class problem. Let's look at the results for recall first of all. So this, remember, we're capturing here what proportion of positive sentences do we actually capture in the data. The best performing classifier for tone is random forest, we find. So we're comparing random forest against the Henry word lists and the Loughran and MacDonald word lists. And we find that the machine learning classifier is good on recall. So it's getting over 9 in every 10 positive sentences from the data. Okay, so that's pretty good. If you want to capture all the positive sentences, random forest looks like it's doing pretty well. The Henry word lists do pretty well as well. So they'll get 7.5 out of 10 positive sentences in the data set. So that's still pretty good. Loughran and MacDonald is pretty poor. So it's only getting 43% of the positive sentences in the data. So it's underestimating the amount of positivity in the data significantly. And I'll explain why that might be the case in a moment. Okay. Precision is then the other side of recall. So conditional on identifying having identified a sentence as positive, is it actually positive? So are you getting it right? So what you see here is actually the word lists perform better than our simple random forest classifier. So conditional on identifying a sentence as being positive, the word lists do remarkably well actually. And Loughran and MacDonald does really well. So it doesn't capture many positive sentences, but when it does tag a sentence as being positive, it's very likely that that tagging is correct. Okay? So there's mixed view about Loughran and MacDonald. It's going to underestimate the number of positive sentences in your data, but the ones that it does classify, it's probably going to classify them correctly. Looks like all the classifiers are doing pretty well. So they're all getting classification performance for positive sentences above 80%, okay, which is pretty good. But the word lists do remarkably well. If we average across that performance, so we take into account both precision and recall, you can see that the machine learning classifier beats the word lists, but it's primarily beating it on the basis that it's capturing more of the positive sentences. Okay? What you see is Loughran and MacDonald is actually quite poor. And this is a kind of potentially important result, because Loughran and MacDonald is the word list that everybody uses, but actually it's pretty poor, and it's poor because it only captures a small fraction of the positive sentences. Let's look at negative sentences, see what performance is there, and things kind of flip round a bit here. So our machine learning classifier only captures 52% of negative sentences. But when it does tag a sentence as being negative, it's very accurate. So 80% accuracy when it's tagged a sentence as being negative. The word lists seem to work in the opposite direction. So the word lists capture a higher fraction of negative sentences, but they are less precise, conditional on tagging a sentence as being negative. And what you particularly see for Loughran and MacDonald is it's really good at picking up a high fraction of the negative sentences. So it's getting almost 90% of the negative sentences in the data. But conditional on that tag, it's getting less than 50% of them correct. So the precision of negative sentences for Loughran and MacDonald is really low. And so what is going on here with Loughran and MacDonald? Well, it's probably because of the makeup of their dictionary. So they have a relatively small number of positive words compared to negative words. And so what that means is they find it hard to pick up a positive sentence, but when they do, it's quite tightly defined, so they're much more likely to be precise. They have a large dictionary of negative words, which means they pick up loads of sentences that they treat as negative. And of course, that will include a large fraction of actual negative sentences. But the downside of that is they make a lot of type 1 errors. So they're tagging a lot of sentences as being negative when actually they're not negative. So it's a mixed story with Loughran and MacDonald, but it's almost certainly driven by the imbalance in their word lists between the number of words in their positive dictionary and the number of words in their negative dictionary. Okay, if you look across the overall performance, so now we're averaging across the two classes, you'll see that the machine learning classifier is typically doing better on average, but the Henry word lists perform pretty well too on average. Loughran and MacDonald comes in at a distant third. And so this is the result that Henry and Leone report in their paper. They report that Loughran and MacDonald performs poorly relative to Henry, and that Henry performs reasonably well compared to a machine learning classifier. But what they don't do in their paper is they don't tell you the level of measurement error. Okay, so we can show you the level of measurement error, and the level is pretty big. So even the best performing classifier, you're getting 20% of cases wrong. Okay, and with Loughran and MacDonald, you're getting over 40% of cases wrong. So there's a lot of measurement error. The other thing to take away from this result that kind of extends the Henry and Leone analysis is it seems like it's much harder to classify negative sentences than it is positive sentences. So negative sentences are associated with lower accuracy than positive sentences. And there might be a range of reasons for that. You know, one is that maybe negative things are harder to explain, so the sentences are more complex. Or maybe it's more obfuscation. Maybe this is capturing managerial obfuscation and you're getting more obfuscation in negative sentences. But either way, it's harder to capture negativity than it is positivity. And of course, that might be quite important depending on the focus of your research design. If you're particularly interested in measuring when managers are using negative sentences, then you're going to be living with quite a lot of measurement error, even for the best classifier. Okay, causal reasoning. What do we find here? Well, our two classes are: is causal reasoning present or is causal reasoning not present? So first of all, let's see what we classify for sentences with no causal reasoning. You can see that all the classifiers work really well. So they're all really good at identifying sentences with no causal reasoning. Okay, so that's encouraging. The problem, of course, is, however, we're not interested in identifying sentences without causal reasoning as researchers. We're typically interested in identifying when causal reasoning is present. So we're interested in the positive category, not the negative category. And unfortunately, our classifiers work really poorly in identifying the presence of causal reasoning. So none of them work particularly well overall. So this is our F1 score. So, you know, we're rarely getting performance above 50%. The machine learning classifier, its recall is poor, but its precision is okay. So it's getting a small fraction of the causal reasoning sentences, but when it does get a causal reasoning sentence, it's more likely to be correct. I suppose the key result to point out here is the Luke word list. So this is the one that's used most frequently in accounting research. The Luke word list is pretty much useless. So it only gets 14% of actual causal reasoning sentences. And conditional on tagging a sentence as causal reasoning, it's only getting accuracy levels of less than 30%. So the Luke word list, although it's a word list of causal words, does not, at least in our data, allow you to identify causal reasoning sentences. And so overall accuracy, if we just look at an overall accuracy measure, well, it depends which one we use. So if we use just our simple accuracy measure, things look pretty good. So we can get accuracy rates of up to 80%. But actually, all that's capturing is the fact that we're just really good at classifying the negative class. Why are we good at classifying the negative class? Because 78% of the sample has no causal reasoning. So all the models are doing is that they're just picking up the majority class. And so you're getting this bias towards the majority class, which biases the overall statistics and hides the fact that the class you're interested in, which is the presence of causal reasoning, actually, we've got really poor classification performance there. These models are still beating chance, with the exception of Luke. Okay, so the unconditional probability is 22%. So we're seeing these classifiers doing better than 22%, but it's still not great. And you're still living with a lot of measurement error. So that's the key point here. There's a lot of measurement error when you're using these automated methods. Attribution type, so internal versus external. Here our sample is more balanced, and our machine learning classifier works reasonably well. So for both internal and external, we're getting pretty good recall and pretty good precision, typically over 70%. So it seems like our machine learning classifier is conditional on identifying a sentence as having causal reasoning in it. We seem to be able to distinguish between internal and external attributions quite well. Our word list, on the other hand, is pretty poor. Doesn't work very well at all out of sample. So that's our results for our 3 discourse features. There's a high level of measurement error associated with all features. Some of them we can classify okay. So we're getting performance up to about 80%, but even then, that's quite a high degree of measurement error, depending on what statistical application you're using. And in some of the measures, so like Lochran and McDonald for tone, or Luke for causal reasoning, we're getting really poor performance. I mean, the measure is dominated by measurement error. And of course, these are the measures we see being used most widely in the accounting literature. So, that's potentially problematic. We do a little bit of further analysis. I'm gonna rush over this because time is tight. Sample balancing is one point when you're training your classifiers that's typically not discussed in the accounting literature, but it can be really important. We've got unbalanced samples, both for tone and for causal reasoning. So we've got a high fraction of the sample is positive and a high fraction of the sample is does not contain causal reasoning. And so that biases your classifiers. And so what you can do in the training process is you can do some sample balancing that potentially improves the performance of your classifier. And so you can use undersampling of the dominant class. So we can essentially match to the minority class and then train on that match data, or we can upsample the minority class so that we get pretty much the same number of observations as we get for the majority class. Does it make a difference? Quickly, yes, it does. So if we look at tone, our majority class is positive. Sample balancing makes no difference. So the black line is an unbalanced sample. The blue and the red bars or different types of balancing, we get pretty much the same result. But it does make a difference in our minority class. So you can see that all the classifiers perform better when we apply sample balancing to train the classifier. And the balancing has different effects on different classifiers. Okay? Similarly with causal reasoning, where we've got the majority class of no causal reasoning, obviously sample balancing doesn't make any difference. You get pretty much the same results. But for the subsample of causal reasoning sentences, sample balancing is really important when training our classifiers. You can get up to kind of 5, 6, 7% better accuracy from your classifier just by training it on a balanced sample. So there's potential benefits to be had in the training approach, but that's not typically discussed in the literature much at all. We do some work on co-occurring features as well, but I'm going to skip that and move to our final test. So this is in a way our attempt at doing an acid test, and maybe speaking to Chris's point earlier about, you know, how good are these automated pipelines going to be overall in testing for things that as accounting and finance researchers we're interested in. So the way we're gonna try and test this is looking for self-attribution bias. So we're going to try and use a combination of automated methods to see if we can capture self-attribution bias in our data. Okay, so if we look at our manual coded data, we can clearly see evidence of self-attribution bias. Okay, so why? Because we're getting a high fraction of internal attributions associated with positive sentences, whereas we're getting a high fraction of external attributions associated with negative sentences. Okay, so this high fractions on the diagonal are classic self-attribution bias evidence. Okay, so in our manually coded data, we can reject the null and accept the alternative that there is self-attribution bias in the data. Now let's try an automated approach where we're going to use a random forest classifier to classify tone and also classify the type of attribution. So this is a very simple approach because here we haven't tried to classify a causal reasoning sentence because it contains so much error. So if we also tried to classify a causal reasoning sentence, we would have no hope of rejecting the null. Okay, so this is like our best attempt at applying automated procedures to test for self-attribution bias. So we're biasing the test in favor of automated methods. And we can see that we're getting a bit of self-attribution bias showing up in the data. So we're getting a high fraction of positive sentences associated with internal attributions. And we're getting a marginally higher fraction of negative sentences associated with external attributions. So there is some evidence of attribution bias in the data, but the significance and the power of the test is actually lower than a manually coded data set. So our manually coded result, which is this one, is actually giving a stronger test than our automated test. And so all this is kind of drawing us to the conclusion that automated methods have a lot of scope. There's a lot of opportunity for doing great work, but you shouldn't automatically think you're going to get a better test using an automated approach. It kind of depends on your research question and the features that you're trying to measure. And it may be the case that in some scenarios, you're actually better using a small sample of manually coded data, as long as the manual coding is high quality. So automated approaches are associated with quite a lot of measurement error. The measurement error varies depending on the discourse feature we're interested in. So tone, we can measure reasonably accurately. Causal reasoning, it's really hard to measure. And we're also getting variation within classification type. So it's easier to classify positive tone than it is to classify negative tone, for example. We find no single automated approach dominates across all the three classification tasks we use. So it's really hard to specify ex ante which method should you use. It's kind of an empirical issue depending on the setting you're interested in and the discourse feature you're focusing on. And we provide some evidence that the amount of measurement error that is generated by some of these automated approaches can be sufficient to generate relatively low power tests. Tests that are statistically less powerful than if you did the test using a manual small sample approach. So, you know, the conclusion is that you're always going to get higher, better specified and a higher power test using large samples and automated methods is not what we would conclude. It's kind of horses for courses. And in some cases, you might get a better test using a large sample automated approach. But in other cases, you actually might be better using a manually coded approach. And so one of the key messages for us, and one of the things we've kind of learned as a result of our analyses, is that, you know, you shouldn't just discard manual coding as being irrelevant. It's actually still as relevant as it always was. And it's very complementary to automated processes. It's certainly not going to be outweighed by automated processes in all settings. Okay, so I think that's me done. I don't know if you've got any other questions you want to ask.
Thank you very much, dear Professor Stephen Young, for your contribution and your effort. It's really excellent paper and excellent presentation. If anyone have any questions, you can open your mic and ask your question. Ahmed Sayed. If anyone have any questions, you can open your mic and ask your question.
Yeah, I got one question about the word list you have used. For example, Lorgan and McDonald's, their word list is very general in business, and mainly it has if you like counts the number of negative words in the word list to the positive is higher. So in earning management, if you look at the positive sentences, then of course you will have like bad results from this word list, particular word list. But if we use it, for example, in risk measurement or risk reporting measurement, it will the result will be better maybe. So it depends. Thank you.
So Mohammed, I think your intuition is correct. I think what we see in the literature is we see people using word lists and applying them to situations where they're either untested or where the ex ante likelihood that they're going to work well is actually quite limited. And so in those scenarios, I think the likelihood is you're going to get a pretty poor test. So I think that, you know, the choice of word list needs to be made very, very carefully. And you need to think very, very carefully about what you're trying to measure and the extent to which the word list is applicable in your setting. And just because the word list has been used on 10Ks in the US to measure tone does not mean that the same word list is going to be great for measuring tone in earnings announcements or IPO prospectuses or UK annual reports or any other setting. Okay, so that generalizability of prior research, I think, is quite limited. And so we should definitely tread with caution. I think that's maybe the key message from our paper. You should approach this area with caution.
I mean, that's an excellent contribution, and I think it was needed in the accounting research to kind of show which approach works. But obviously, as you said, we need to be very careful on what is the subject and the method that we are investigating, right? Because this might be true, and all those coefficients and the differences works for your earnings performance, but it might not work for an 8K filing or for a proxy statement or any other type of filings.
Yeah, I think that's absolutely right. And I would, the analogy I would give to a lot of the work that we're seeing in textual analysis in accounting at the moment is, I'm old enough to remember when researchers started measuring earnings management using discretionary accruals. And that was a very attractive measure for researchers. And similarly with things like conservatism using the BASU model, they were very attractive measures because they were simple to use. So they kind of democratized research because it made it possible for anyone to measure these constructs quite easily. The problem, however, with that is it's almost too easy to use these measures, and people don't think carefully enough about the applicability of the measures and what the measures are doing. And I think that's quite dangerous, particularly for junior researchers, because they can be tempted to think that these approaches are reliable when actually there's quite a lot of pitfalls associated with them.
Yeah, and so I do a lot of this research, and so again, it's kind of like poking me a little bit, right? But but ultimately, I just think that we have to be very clear that what we're measuring is a proxy for something, and again, if it's counting number of positive words less the negative words divided by positive plus negative words, right? That is something, right? The construct is something. Measuring it under a bag of words approach is something. You just have to be careful, as Stephen is saying, to not, basically say that it is, manager's tone, whatever it is, right? It's a proxy for something, right?
Yeah. You're absolutely right, Chris. And I mean, I think what we know from prior research is that it's clearly measuring something, because prior research shows us that we get consistent relations in ways that we might expect theoretically. So it's not that these measures are useless, that they're clearly capturing something, just like a discretionary accrual measure captures, something. But the key point for you guys, if you're interested in applying them, is just being wary of what they're capturing and making sure that you don't overstate or overplay what you think you're capturing. Yeah, I think a bit of healthy.
Or as I pointed out, I mean, I think a lot of people, Stephen talked about how easy this is, right? It's not that easy. Like, people think they can take a 10K and break it up into its various components. I'm telling you, it's not as easy as you think it is to find the footnotes. Like, go find that tax footnote consistently in a 10K. And again, you're a pretty good programmer if you can do that. And I just think there's a lot more bias. So Stephen is already talking about, like, once you have the sentences, how hard this is. My earlier comment was saying just finding the sentences is hard enough, right?
No, you're so right, Chris. And I mean, we worked on a project extracting text from UK annual reports. So this was extracting text from PDF annual reports, unstructured documents. So not having the sort of 15 sections in a 10K. And we worked on the project for about 6 years, and we've got a model that kind of works okay, but it's a lot of work for an okay result. And you're absolutely right. It's really, really hard to do. And I think a lot of the papers that you see published, they don't really give a sense of how difficult it is and what the pitfalls are. They present it as if it's pretty straightforward and it's pretty accurate. And I think that is a bit of a problem, because it just gives this sense that this is straightforward to do and it's reasonably accurate. And yeah, as Chris is pointing out, it's incredibly challenging.
Yeah. Hi, Steve. Can you hear me?
I can, yes.
Yeah. So I'm sorry, I've just come a bit late. I'm wondering from or your data. Did you get your data from the UK or from US and yeah.
Yeah, so our data is a UK sample, so it's earnings announcement statements by UK firms.
Yeah,
So
and is it taken from the annual reports or from the earning release?
yeah, it's taken from the earnings release. So we've
Yeah.
we just capture the we just got the HTML file of the earnings release.
Yeah, so this takes me to my question, which is, do you think your conclusion will still or can be generalized if we repeat this analysis in terms of annual reports, or if we move to the US, especially considering the fact that the US 10K is structured compared to the UK release and so on?
So yeah, so it's an important question. I mean, our paper doesn't really deal with the challenge of grabbing the right sentence. Okay, so our paper is pretty silent on the extraction problem.
Yeah.
Our paper is about conditional on having got the data you want. How accurately can you code it? I think that question about how appropriate is it that you can apply these methods to a 10K or to a UK annual report, that's partly what Chris was talking about. Part of the challenge there is actually about getting the data and focusing in on the bit of the narrative that you're interested in, and that's a separate natural language processing problem. So you can think of this textual analysis work as really being two problems. One is about go on, Mohammed.
There is another question from.
I'll just finish that. I'll just quickly finish that point, Mohammed. Yeah, what we found is this textual analysis work is really about two research problems. One is about actually getting the text. So can you get the right text that you're interested in, whether it's the footnote, whether it's the chairman's statement, whether it's the MD&A, can you get the bit that you want to analyze? That is a separate challenge, and it's non-trivial. It is really difficult. And that was Chris's point, and that's our experience as well.
I agree. I completely agree with you, but I believe that I think you should have or mention a limitation for this research, which is because in the paper you argue that the Lauren and McDonald word list is doing or is performing very bad, but I believe the story might be completely different if we consider the 10K instead of the earnings release. I believe so, and also our prior research indicates that using Lauren and McDonald word list in the UK context is or has many limitations. So to find that Lauren and McDonald word list performing very bad in the UK. So yeah, this makes sense. Also, another something which gave me some confusion is you have used both the Henry word list on 06 and 08. And for my understandings, both or these two word lists are identical in exception with one or two words. So to find significant
they're pretty much the same. Yep. So but you know that I think there are about 4 or 5 words that are different.
Yeah.
And so we have no priors about which is best, so we just use both.
Yeah. Thank you, Steve.
Just on your point about Loughran and McDonald, Mohammed, because I think this is an important point. I mean, the Henry and Leone paper in Accounting Review.
Yeah.
They also conclude that Loughran and McDonald underperforms the Henry word lists.
Yeah.
Now, what they don't tell you is accuracy levels.
Yeah.
But I mean, to be honest, I have no reason to suspect that Loughran and McDonald is materially better in the US than it is in the UK.
Yeah, and even in the US, I remember that Lauren and McDonald themselves indicate that their word or their positive word list is doing it is doing not good in even US. So yeah, but yeah, all in all, yeah. Thank you, Steve. Thank you so much.
Okay, my pleasure.
There is another question from Machine Dean. Yeah, you can ask.
Oh, sure. I thank you, Professor Yang. I just have a simple question. So when we're saying the test you have on the classification of the causal effect, you mentioned that the method of the LIWC, the word list is performing extremely bad. And I was just trying to understand like how so, because you were doing that also manually. And are there, for example, are there many like a lot of words that were not captured in the word list, or like how can it be?
So, okay, so yeah, it's a good question. So what we found is that the Look word list works okay for sentences where it's a simple causal statement. So when managers say profits are up because of, or results are down due to, it works well, okay? But unfortunately, what we find in our data is that a lot of causal statements are actually quite sophisticated linguistic constructs. So the sentence is not simple. And as a consequence of that, the Look word list really struggles. So there are, words like because and due to and result, like as a result of, they are pretty common words in sentences. And so part of the problem with the Look word list is every time it sees the word result, it treats it as causal reasoning, whereas it there's a high proportion of sentences where that word does not indicate causal reasoning. So it's really just that the language construct of causal reasoning is much more sophisticated, and so a simple word list, it finds it really hard to disambiguate that complexity.
Okay, sure. Yeah, that makes sense. Yeah, sorry, because I'm just quite new on this topic of textual analysis, but I do find it interesting. But then, are there word lists that actually includes the degree of negativeness, like of the word? Because I mean that will help.
Yeah, and so you're absolutely right, and I think this is where there are lots of opportunities for researchers to do really interesting things. Rather than just taking Loughran and McDonald's word list and applying that in your data, I think there's lots of opportunities to train and test and develop domain-specific word lists for particular research settings where you're going to get much more accuracy and much more power, and that in itself will be a useful contribution to the literature. I think one of the problems that our research is suffering from at the moment is as soon as someone wants to measure a particular feature, they just go off and use the most popular word list that everyone else has used, and unfortunately that may not be the best option.
Yeah, I agree. But then besides the word list, the structure also matter. And yes, you also mentioned like a deep learning is actually a better, I feel like it be a better way to also decompose like the sentence.
Yeah.
Yeah.
So you're absolutely right. So that set of results that I showed you at the end, where we've got some self-attribution bias.
Yeah.
So we've applied a deep learning model to that,
yeah.
and we can replicate the manual result using a deep learning model, but we can't replicate the result using simple classifiers.
Sure.
Yeah. So you're absolutely right. If you're going to do this and you want to do it properly, there are cases where you probably need to do more sophisticated things than use a very basic classifier and a bag of words approach. That will get you so far for some research questions, but for more interesting research questions, you probably need to use slightly more sophisticated approaches, or you need to do some manual coding. There's nothing wrong with identifying a set of firms and coding it manually, as long as the manual coding is transparent and objective. That's the key.
Yeah, thank you. Or do you think it's possible that the accuracy will improve with the data size goes larger?
I mean, if you're using a training algorithm, then yeah, a big data set, all else equal, will probably give you, it gives you a better chance of training. But you know, the quality of the classifier is also determined by the choices you make in applying the classifier.
Mm-hmm.
And the type of classifier you choose. Yeah, so it's a mixture.
Yeah, sure. Thank you. Yeah, that's all my question.
Are there any questions? If anyone have any questions, you can open your mic and ask your question. I think that you have done very well with answering a lot of questions there, dear Professor Stephen Young. So thank you very much. And it's all that remains for me to say is thank you everyone that joined us, and I thank you very much for taking the time out to present to us today, dear Professor Stephen Young. It has been really appreciated.
Thank you, Mohammed. So thank you ever so much for the invitation. Thanks to everyone for your questions. A couple of people asked in the chat for my email, so I've put that in the chat. I'm sending the slides to Mohammed, so if any of you want the slides, Mohammed will be able to share those with you. Okay, and thank you very much. If you've got any questions and you want to follow up, please do not hesitate to get in contact with me.
Thank you very much, dear Prof. Stephen. I hope to see you soon in Egypt.
My pleasure.
Thank you.
And thank you to everyone.
Thank you very much.
Thank you,
Bye.
Dr. Self, for this invitation.
Bye-bye.
Goodbye. Goodbye.
Thank you, Dr. Self.